Hello, everyone. My name is Zachary Charles, and today I'm going to be talking about some exciting work that we've been doing here at Google on adaptive federated optimization. And this is joint work with a lot of great people at Google. Sashank, Manzel, Keith, Zach, Jakob, Sanjeev, and Brendan. I don't have too much time, so I'm going to get right to it. First, just an overview of what adaptive federated optimization is all about. And really, the goal of this work stream is to improve optimization methods for federated learning, FL. And at a high-level view, what this is about is we want federated learning methods that automatically adapt the client and server training to heterogeneous user data. For those of you not familiar with federated learning, just remember that it involves the server broadcasting a model to clients, the clients doing some local training, that's A. B represents kind of all the different heterogeneous client models that are then sent to the server again, and that is used to update its own model. And so really what we're about here is the idea that different clients are going to have very, very different data in federated learning. And this makes optimization a challenge, especially because federated optimization is a really new area that I think I would go out on a limb and say that not too many people have real good intuition about. And so we tackle this problem to some extent, and our main contributions are as follows. We develop novel and practical methods for federated optimization. We benchmark these methods on a really wide variety of tasks and models, and we provide an open source implementation of all of this within TensorFlow Federated. And so just some things that are important here. Two of the difficulties in this workstream were hyperparameter tuning and kind of a lack of consistent benchmarks in the field, and I'll get to that. So research overview. Federated optimization is something that really occurs in two different levels. There's client optimization and server optimization. So this diagram kind of gives a very high-level view of what's going on. The server model here gets broadcast to the clients, and the clients do some local training. That involves the client optimization. Now, once the clients are done training, they send their model back to the server. The server takes all of the client updates, and it somehow updates its model. This is where the second level of optimization, the server optimization, comes in. In federated averaging, if you're familiar with that, it does a really simple update. All it does is average the client updates and use that as its new model. But you can imagine doing something more sophisticated where we try to use stochastic gradient descent using these client updates as a kind of estimate of a gradient. And so what happens is that just by restricting to federated averaging, you might be hurting yourself in heterogeneous settings. And this is particularly true in natural language processing, where a domain where users have very different vocabularies. So over on the right, I have a plot. This is a next word prediction task, and it's on a realistic heterogeneous data set. And we've plotted here what happens if we use SGD on the server versus SGD with momentum on the server. The clients just use SGD. And this is with tuned server learning rates and client learning rates. And what we see is that there's this huge gap between what happens with standard SGD and what happens with SGD with momentum. And this really begs the question, what else can we do? What if we start using even more sophisticated methods for optimization within our federated setup? And so we just devised a general framework for federated optimization that explicitly accounts for client-server optimization. And it recovers a lot of really popular methods such as federated averaging. We call this FedOpt, and you should really think of this as a collection of algorithms. And what's really important is that FedOpt incorporates a client optimizer. You get to pick what you want. That happens on the clients, obviously. And a server optimizer. That's the optimization happening at the server. And what's really important about this is that client optimization is fundamentally different from server optimization. In a lot of settings, clients only participate at most once because there's so many clients. Clients generally only perform a small number of steps, whereas the server is present throughout, and it can hold on to things in memory, so it can preserve state throughout the algorithm. And this makes the choice of client optimizer and server optimizer very different. What you're looking at is that the server optimizer might be better suited for very sophisticated algorithms. And this is exactly what we do. We incorporate adaptivity into the server. And the reason that we use adaptivity is that adaptive methods are really, really important in a lot of machine learning contexts. We've seen this explosion in the use of methods like ADAM and AdaGrad, and now there's all kinds of variants that have, pros and cons. But these are undoubtedly important to the empirical success of machine learning methods. And so what we do is we incorporate this adaptivity into our federated learning experiments in a way that is theoretically justified and empirically justified. And we provide easy-to-use open source implementations that really are about benchmarking and making reproducible our results. And so what I've shown here, this is the update for AdaGrad that involves this kind of preconditioner matrix that is learned according to the heterogeneity of your coordinates. This is a coordinate-wise update rule, and we incorporate this onto the server. So the results, accomplishments. We designed 3 new adaptive federated optimization algorithms. We call them FedAdaGrad, FedYogi, and FedAdam. And these are versions of our framework where the server uses an adaptive method such as AdaGrad, Yogi, or Adam. Yogi, for those of you not familiar, by the way, is a variant of Adam that involves kind of a more conservative approach to changing the learning rate, and has had a lot of great empirical success recently. And so we analyze the convergence of these algorithms, and we show that they are justified, and that they can recover essentially the same asymptotic convergence rates as mini-batch SGD. And the fact that the asymptotics are the same shouldn't be too surprising, in the sense that AdaGrad, for instance, has a similar asymptotic convergence rate to SGD in the centralized setting. But where things start to get improved is in kind of non-worst case scenarios when you actually are dealing with sparse data. And so we'll get to the empirics, but these methods generally perform much better than just SGD. So like I said, we implement these in an open source way on really 6 different tasks. And so this, we use 4 different data sets. We use CIFR100. We train a ResNet with group norm layers. We use this EMNIS data set, which is a digit recognition data set that is naturally heterogeneous, partitioned according to the writers of characters. We do digit recognition and autoencoder tasks on it. We use the Shakespeare data set, in which each client corresponds to an acting role in a Shakespeare play, and the data are their lines. We do next character prediction. So character is in A, B, C, D, that kind of character. We also use the Stack Overflow data set, which is a collection of posts on Stack Overflow. So the clients are users, and their data are their posts. And so we do 2 different tasks there. We train an RNN to do next word prediction. And we also use a logistic regression classifier on bag of words vectors to do tag prediction. And what's important is that this is actually now a convex task. So it's a good way to see behavior on different kind of loss functions. So let's get into what the actual empirical results are. Basically, what we found is that adaptive optimizers significantly improve upon non-adaptive ones in a lot of different tasks, and do at least as well on the non-adaptive optimizers on all tasks. And so I've plotted 4 of the results here. I think these are the 4 most important in the sense that I've omitted the EMNIS ones because EMNIS is kind of a simple data set and it's pretty easy for most optimizers to do well. So on Shakespeare, what we see is that FedAdaGrad, which is this federated version of AdaGrad, is actually much better initially than other methods, and eventually ends up being a little bit better than other methods such as federated averaging. CIFR100, we see a similar story where federated Yogi and FedAdam do really, really well. And they actually do a couple percentage points better than federated averaging with momentum on the server. That's what this FedAverage-M is. And much, much better than federated averaging. Note that we do see FedAdaGrad kind of fail here, and that's because this is a very non-convex task. It should be noted that image classification is something historically that SGD with momentum is really, really good at. So it's not surprising that FedAverage-M does really well here. However, once we get into language modeling, things become much different. So for instance, this is the Stack Overflow logistic regression task. This is the tag prediction. We've plotted the recall here. And we see an absolutely huge difference in what's going on with the non-adaptive methods, that is federated averaging, FedAverage-M, and the adaptive methods. And what's going on here is that some of the tags are so infrequent that when federated averaging, FedAverage with momentum see them, they don't make enough progress. And so this adaptivity is really, really important to make progress on clients who have rare tags. We see a similar thing on next word prediction. And again, it's these rare words that we're really seeing the benefit of adaptivity. And so we have a table here kind of showing the best result within a couple tenths of a percentage point for each task. And really what we found is that FedYogi did at least as well as all the other algorithms throughout. And so this code is available for comparisons externally. Yeah, so if you have a desire to use it, please do so. And please contact us with any questions. So some future work. This was adaptive server optimization that I talked about. And you might imagine that, well, what about adaptive client optimization? That might seem much more natural. This is a hard thing to incorporate, though. Clients usually only take a couple steps. And now, since they don't necessarily maintain state, especially if you imagine that they're smartphones that just participate once in a while, you're going to have to learn the preconditioner in a very federated manner in which you're going to have to do extra communication somehow to learn what this preconditioner is going to look like. And so it's an ongoing question of how exactly are we going to incorporate client adaptivity. And we think that we can combine it with compression and kind of an extra communication step for this preconditioner that will allow us to learn a better preconditioner matrix in a communication efficient way. I am running out of time, so I'm going to skip this next open area and just move on to the future work. I just want to highlight that adaptive federated optimization can be used in tandem with other areas of research, such as differential privacy, compression, personalization, or your research area here. And some open questions are, how do adaptive optimizers affect privacy and utility of differential privacy? How about fairness? Do they encourage fairness by allowing clients with unseen data or like very infrequent data to make a lot of progress? And also hyperparameter tuning is really important. I didn't get a chance to talk about it, but it can be hard in federated learning. And so really we're interested in ways of making this easier. So just in conclusion, adaptive optimization methods have shown great promise in both simulation and in practice. These methods have the potential to benefit many topics in FL. And we're really trying to bridge FL theory, simulation, and practice. And so if you're interested in any of this work, please contact me or attend the live Q&A session. Thank you.